Now, next talk we're going to have is from a car hacker who doesn't drive a car. So he rode a bicycle to get here, and he's going to talk to us all about car hacking. Now, the reason I'm really excited about our next speaker, his name is Tomer Fichman. Tomer started off as a BSidesTLV attendee. He was at BSidesTLV 2019. Give it up to him. Woo! Yeah, that's Tomer right here. And now he's a speaker, so you too can join us up on this stage next year if you want to. So Tomer started as a participant, now he's here on stage. And Tomer is, let's give a good smile for the camera. That's nice, thank you, Shlomi. So Tomer here is gonna take us through car hacking and insecure boots. Now, there's all kinds of boots. There's boots like this, there's the trunk of your car, and there's the boot that loads up your operating system. Which one are you gonna talk about?
The insecure one.
The insecure one, that's perfect. Stage is yours, Tomer, take it away. It's a deep dive into car hacking.
Woo! So, hello, BSides. I'm very excited to be here. As Karen said, I'm a long-time S&D, and it's very exciting to be here on the other side of the stage. So, welcome to my talk, Insecure Boot, Finding and Exploiting Vulnerabilities in Renesas Secure Boot Implementation. In this talk, I'm going to talk about vulnerabilities affecting millions of cars and other devices. These vulnerabilities will allow us to fully bypass secure boot and run malicious code on the target. So, next. Some technical issues. Okay, thanks. So, who am I? My name is Tomer Fichman, and I'm a security researcher at Simotive Technologies, which is a company that does cybersecurity for smart mobility, which is a very fancy way of saying car hacking. I work in the embedded PT team, which basically means hacking away at car-related ECUs by way of code review or reverse engineering. And in my experience, I've done vulnerability research, reverse engineering, and malware analysis. Okay, my mistake, I was moving backwards. Anyway, the agenda for today. So today we're going to talk about the background and motivation for this research and of secure boot. We're going to talk about how Renesas implemented their own secure boot mechanism. We're going to go over the vulnerabilities I found there and how to exploit them. And more specifically, we're going to go over 4 vulnerabilities and exploit one of them fully to bypass secure boot and execute malicious code. Then we'll go over the fixes issued by Renesas themselves and next steps for research. So, it all started on a code review project abroad for a client. Our target was an infotainment unit, which is the little screen thingy over there where you play music on your car. And the topics for the project included redacted due to NDA, redacted due to NDA, and secure boot, which I got. Cool. Except that, what is secure boot? Because at the time of the research, I had near zero experience in that area. I never researched it before, which is a good time to mention that I'm by no means an expert on the subject. I just did one nice research project about it, and I will share it with you today. So with that, what is secure boot? Well, basically, it's a mechanism its goal is to make sure that the platform will only execute trusted code. It does this by establishing a chain of trust where each image will verify the next image in turn. For each image, a signed certificate will be manufactured containing the hash of the content of the image and the destination and length of the image to be loaded into memory. And each bootloader stage will load the one after it, verify everything, and will only pass execution if all the checks will pass. So let's go back to our target, the infotainment unit. It was running on an R-Car automotive system on chips made by Renesas, which is a leading automotive SoC manufacturer based in Japan. Now, because the target was using that SoC, it was using also their secure boot implementation, which is open source and made by Renesas. And that one in turn was based on the ARM TFA, ARM Trusted Firmware one, which is a secure world software reference implementation made by ARM, which is a whole other thing by itself. But basically, its goal is to have a system running where we have our non-trusted world, which is running a rich OS like Linux, and a trusted world, which is where we keep our sensitive information that we don't want to get compromised, even if the rich OS itself is compromised. Their equivalent of secure boot is called trusted board boot, and it is used by many reputable manufacturers such as NXP, Texas Instruments, ST, and more, and of course Renesas, which we will talk about today. So, specifically the part we will talk about today is the BL2, the second stage bootloader, which will load 3 images, BL31, 32, which are the secure world images, and BL33, which is the Linux non-trusted one. We will be focusing at the Renesas code, not the ARM trusted firmware one. And what BL2 basically does, as you can see here, is loop over a list of image IDs to load and verify them, load them to memory and verify them, and then pass control to the next image in the boot flow. We will also specifically look at the attack surface that happens before the verification itself, because that would require us either to attack the crypto mechanism itself or having a signed certificate for an image, which greatly reduces our ability to attack that. Anyway, so before any loading will happen, we have some pre-image load checks. Here is a pseudocode of what will be done. First, we will read the image certificate into memory. Then we will load the destination and length of that image from that memory. And eventually, we will check whether the memory area in which the image is to be loaded from the certificate is an allowed one. In this case, we can see the check for BL31, which will check it against the base and limit of it. So, yeah, continue. So, the first thing that we said was reading the destination and length from the image. We will get the certificate as a parameter, and we need to populate the length and destination. Now, we will take an offset into the certificate, read the size from it, multiply it by 4, and save it in len. I guess it's a conversion from number of D-words to number of bytes. Anyway, the problem here is that we take a 32-bit integer, multiplied by 4, and save it inside another 32-bit integer, which will, of course, will result in an integer overflow, which is our first vulnerability for today. Unfortunately, this issue is not very useful, as the overflow is consistent across uses of that len variable, meaning we don't have any mismatch between the calculated length and the actual length, and any buffer overflow that could happen as a result of that. But it did motivate me to keep looking deeper inside the code base, and it could hint at other arithmetic issues hiding nearby. So after we had loaded the destination and length, now it's time to check it against the allowed one. This is important because if we will just allow any image to be loaded anywhere into memory before any verification on it is being done, we could just overwrite the stack, for example, and get code execution that way. So it's important to verify before we do any kind of loading. Now, this check load area function will be called for every bootloader images, except for BL33, the Linux one, which is very curious and was surprising to me because I said it's not very safe to just load anything anywhere. But when I dug deeper inside the code, loading the actual images, I found this curious check, where if our counter reaches BL33, then we have a special check being performed. So it's a very weird way to hide the check later on inside the boot flow, but there is a check being performed over there. Okay, let's have a closer look at it. So, as I said, this function will receive the dest and length variable. And it's important to note here that, once again, this dest and length variable were read from the certificate, which is attacker-controlled. It is not being verified anyway. It was read from external from the external memory, and assuming we have access to that memory, we can maliciously affect the contents of the image and the destination and length at this point. So the first check is whether the destination, which is the base of the image, is before DRAM start, before the start of the DRAM memory range. Second check is whether the dest is larger than DRAM minus length, which is mathematically equivalent to dest plus length over DRAM end, which basically means will the image end after the memory range. Okay. After that, we check against some protected memory range. We check whether we start after prot start or before prot end, meaning whether we start loading the image in the middle of the protected area. And after that, we check whether we start before the protected area and end inside it, overwrite into it. So basically, we can see that these checks, the goal of this check is to see that we will be loaded inside the DRAM memory area, but not inside the protected one. Okay, what's inside the protected one? We will get to that later, but interesting stuff to overwrite. But what if len was larger than prot start? Well, because it is being subtracted from it, it would actually cause an integer underflow, causing it to go to be a very large value, larger than dest, of course, which would cause the fail to check, and which would cause the if expression to be validated to false, and the entire path to check. Cool, so we have our second vulnerability, and it is the overflow, which will allow us to bypass this check. And bypassing the check will allow us to start before prot start and overwrite inside it and overwrite interesting stuff there. So let's better understand our primitive here. Okay? First of all, can len actually be larger than prot start? Can it actually underflow it? Well, of course it could, otherwise I wouldn't be talking to you about it. But let's see how. So len is a 32-bit integer, as we have seen previously in the first vulnerability. Now, what is prot start? Well, that depends on another variable called legacy, which is basically, does this image operate inside a 32-bit address range? Does dest plus length is smaller or equal to uint32 max? If it does operate in a 32-bit range, well, then prot start will also be a 32-bit value. If it's larger than that, it would be a value larger than uint32 max, meaning we won't be able to underflow it. So the first constraint on our primitive is that we need dest plus length to be smaller than 32-bit. Okay, next. If we are in legacy mode, these will be our values for prot start, DRAM base, and DRAM end. So now let's see which dest and len values we need in order to pass all these checks. So if we want to pass this check, we need dest to start before prot start and len to overflow prot start. So let's just take dest to be 4 less, len to be 4 more, and we should be able to pass that check. Cool. Next, we want to check this, pass this check. If dest is before prot start, we will pass this check. And lastly, we still need to be inside the DRAM memory area. Well, it is large enough to start before prot start and have a length larger than prot start, and we would, this would be valid to false, which is what we want to happen. Cool. So remember I talked earlier about overwriting the stack, which would of course be like the go-to thing to do if you just have an arbitrary write. So can we smash the stack? Well, if we look at the values, once again, for DRAM base and DRAM end, and compare it against stack base, the stack base is after DRAM end. Meaning that if we want to actually write to there, we would need to overflow DRAM end in order to pass the check. But in order to underflow DRAM end, we would need to have a value larger than it. And in order to still stay in legacy mode and have a value that is underflowable, dest would need to be this 3FFFE, which is smaller than DRAM base. So it would fail the other part of that expression, meaning we cannot override the stack. Another reason we can do it is because DRAM area is from hex 4, a bunch of zeros, up to hex C, we said, and the system RAM area x63, where the stack is not mapped all the way between there to there, so we probably would have failed on trying to write to unmapped memory anyway. So the stack will remain unsmashed for today, and let's go back to overwriting the protected area. So I promised interesting stuff, and here they are. Inside the protected area, we have 3 interesting stuff. Here is a simplified memory map of that area. At the base, we have our certificates, the very one that will be used later on to verify the contents of our secure boot image. After them, we will have BL31 and BL32, which, as I said, are the 2 other images to be loaded, and they are the secure world part. So basically, we can overwrite the certificate, BL31, BL32, all of them together, and have a lot of fun. So if we override the certificate, will that actually help us to pass the checks later on being done in the secure boot? Well, let's look at how the image will be verified later on. Well, first we have our load image, which is what we looked at now, where the underflow happens and the image will be loaded and overwrite the protected memory area. And then we will call the function to verify the image. Now that function will receive the image ID, the destination, and the length of the image just now loaded. But it will actually ignore the depth and length parameters when verifying the image, and it will just read the certificate again from memory and call some secure boot API function to verify it. So that's interesting in a few ways. First of all, it doesn't matter where we just loaded the image into and what our certificate was. The secure boot API will load the certificate again for memory, and it will be the only thing that is passed for verification, meaning it will read the depth and length from there again and verify it against the certificate. Also interesting, the secure boot API is not part of the open source code, but a function in bootrom, a closed source one that Renesas did not allow me to review or share with me. So it's something interesting to look at more in the future. So let's recap a bit the attack here. We will load the image, which will use our malicious certificate and the destination and length inside it. We will override that certificate by exploiting the vulnerability. We would then call osmod verify image, which will load the new overwritten image, verify it, and pass the check. Another question here is, will the BL33 entry point be heard from this? I mean, eventually, the bootloader needs to hand off execution to the Linux image, and if it tries to read the entry point by using the destination from the certificate, it will read the wrong one because we overwritten it, and it will fail. So fortunately, this value was read and saved at the start of the run and flushed as a parameter to the next stages, so we will be fine from that angle. Cool. So let's put it all together, the entire exploit for this issue. First, we will take the existing Linux image and modify it in our own malicious way. Then we will read the current certificate because we will later use them for overwriting our own. Then we will craft our own BL33 certificate with a len larger than port start and a destination of, let's say, port start minus the size of the Linux image, so that we will write the entire Linux image, and then right where it ends, we will overwrite the certificates. And after that, we will put inside the image data, I said, the Linux image and the certificates. And that's it, that's the entire chain to fully exploit it and get code execution on the devices running Renesas Secure Boot. We will not be having a demo. And we will skip that part. Okay, so after we've gone over all of these issues were reported to Renesas, of course, and they issued fixes for them. So let's take a look at one such interesting fix. Okay, remember at the start I told you we will be looking at 4 vulnerabilities and exploiting 1? Well, we looked at 2, exploited 1, and now we have the rest. Because in this one commit to fix the issues reported, Renesas has managed to introduce 2 new vulnerabilities in their code base. So let's start with what this commit even does. So as highlighted over there, the goal of this commit is to check if the next image invades a previously loaded one. As we said, our attack, one attack path we had was overwriting BL32, for example. So this check aims to see that we will not be able to overwrite any already loaded and verified image in memory, which is like an logical thing to do. So the first issue was the way they implemented the checks. You can see they checked whether we start in the middle of an image. With more context, each destination length will be saved inside an address-loaded array, and then looped over that array, and we check our current destination length against all the previously loaded ones. So we will loop over all the images, and we'll check whether our current image base dest is inside that of another image, or whether we start before and overwrite inside another, just like the previous checks we have seen. But what if destination is equal to that of a previously loaded image? Well, in that case, all these checks will pass, and we would be able to overwrite the image. So that's the first issue they had here. And after I found it, I went to my colleague, Eli, who is here in the room. Shout out, Eli. For some human rubber ducking, as I usually often do. And I told him, what do you think about this issue? Does it look vulnerable to you? And he said, yeah, that looks fine, you know, but there's another vulnerability here that you have missed. And he was right. There was actually another interesting thing here that I should have seen, because if we look more closely at these parts, we can see that address loaded is an array of size check image area count, which is defined as 5 here. And address loaded count is initialized to 1. And before we actually do all these checks, we check that our address loaded counter is not larger than 5, which is the size of the array. And if it is, we will have set the result as failure, which would eventually cause the entire boot flow to be aborted. But before the boot flow will be aborted, we will still use this out-of-bound index to write inside address loaded the destination and length, causing two out-of-bound writes. Now, even more interestingly is the fact that after address loaded is the address loaded counter, which makes it probable, but depends on the compiler, that they were compiled right one after another in memory, which means that the first overwrite of dest would overwrite the counter itself, causing the first overwrite of len to actually be of any relatively positive offset to address loaded, which is a very fun primitive to have. So we reported to Renesas these vulnerabilities as well, and they fixed them. Cool. Impact. So, as I said, in order to exploit these issues, we would need to be able to actually change the images in memory, which means we either need to have a high privilege in the rich OS Linux, high enough to overwrite the images in Flash, or have a physical access to the memory where they are stored to change them there. And what can we get with these primitives and this vulnerability? Well, we could break separation between trusted world and non-trusted world, because as I said, we could have overwritten BL3132, which are the secure world images containing sensitive data. And we could also have just used this as an initial access vector into the device by exploiting it to write malicious Linux image, as we have demonstrated. Cool. Impact. Okay, so we've seen what we can do. Let's see what we can do it on. So as I said, the initial research was done on an infotainment unit inside the car, and the R-car SoC families, as seen here, is used for anything from cluster dashboards up to autonomous driving, but the code base is shared also for the RZG family of Renesas, which is used for HMI and IoT applications, such as point-of-sale systems, electrical vehicle charging, industrial gateways, and many more stuff. Cool, so timeline for these issues. Well, the initial research was done in November 2022, where the certificate length overflow and checkload area underflow were found. In January 2023, the faults were reported to Renesas, and in March, they issued the first round of fixes. Shortly after that, I found the address range exploitation and Eli the address buffer overflow vulnerability, and we reported them to Renesas as well. And in April, they were also fixed and pushed to the public Git repo. And hopefully, somewhere around this year, CVEs will be issued for this vulnerability. We are in the ongoing effort with ASRG, which is the CNA for automotive-related security vulnerabilities, which means that they are responsible for issuing CVEs for that area. And okay, what's next? Well, research-wise, looking for similar vulnerabilities in other secure boot implementations could be interesting. Also, researching other driver code could be more prone to issues, aside from the main ARM-trusted firmware code. And also researching the boot ROM code, which is where we saw the actual cryptographic verification of the certificate and the image being done. Cool. And personally, for me, what's next is I'll be traveling through Central and South America for 6 months, so don't expect any new research from me. And a blog post will go up in the SciMotive site. Thanks. Thanks to Eli for finding the false vulnerability and being my rubber ducky. Thanks to Matan and also Tomer and Benny for feedback on the presentation. And, I went too far. And to the Renesas PSIRT, which is the Product Security Incident Response Team, for issuing quick fixes and being very cooperative. And thank you for listening to me talk for 30 minutes about secure boots.
Amazing. Thank you so much, Tomer. You did it. Amazing.